Hi, everyone, and welcome to Lesson 7 of Unit 4. And in this lesson, we're going to introduce the idea of acids and bases. Just a little bit about some of the background theory behind acids and bases, and then specifically into this idea of strong versus weak acids and bases. Okay, so let's get started. Essentially, um, acids and bases are very important to many aspects of our existence. Certainly from a biological standpoint, but also from an industrial standpoint. You're going to see that acids and bases are everywhere. And they fit well into this unit of solutions because in many cases, acids and bases are um, dissolved in water. And so they don't have to be, but in most cases you'll see that they are dissolved in water and therefore they are a solution. Okay, so a couple key points here. They obviously we use them in the laboratory. Hopefully in grade 9 and 10, you've worked with acids and bases a little bit. Maybe you've dipped a litmus paper in them to test for acids and bases. And so on. In everyday life, acids and bases play a role in everything from digestion of foods you eat to the function of the medicine you take and even the cleaning products you use. Without acids and bases, many of the products in your home today would not have much use. I've given you this table here, just to show you that acids and bases are everywhere. They're in citrus fruits, that's citric acid and sorbic acid. In dairy products, lactic acid. Vinegar is essentially a dilute form of acetic acid. In soft drinks, we have carbonic acid. The odor some of the odor that you give off is a certain type of acid, acidic. 3-methyl-2-hexanoic acid. Bases, oven cleaner is sodium hydroxide. Baking soda is sodium hydrogen carbonate or sodium bicarbonate. Washing soda, sodium carbonate, and glass cleaner is ammonia often. So these are examples of acids and bases that you've probably come across on a regular basis. Okay, so properties of acids and bases. I think many of you have probably seen some of these properties. We've done some labs with them in grade 9 and 10. Acids, so in terms of taste, tend to have a sour taste to them. And if you can think about, a lemon, it's a very sour taste, whereas bases have a bitter taste. And some of you may not know the difference between those, but soap is a base. And so if you can think about soap in your mouth, hopefully, you don't get that very often, but soap, it tends to be bitter in its taste characteristics. Both acids and bases conduct electricity well because both of them form ions. And so we've seen that any solution that is formed with positive and negative ions, they conduct electricity well. And the feel, the characteristic feel, well, acids don't really have any feel, but bases feel slippery. So if you were to put your fingers into a basic solution and obviously not of strong base, because if it was a strong base, it would burn your fingers, but a weak base would feel slippery. And a good example of that is soap. Soap feels slippery to the touch. Okay, a few more properties. We often use something called litmus paper to test for acids and bases. Acids turn all litmus paper red. So you can, just so you know, you can have different colors of litmus paper, but if regardless of the color, when you stick it into the acid and pull it out, it'll come out red, whereas bases turn all litmus paper blue. Okay. Acids react with metals to produce hydrogen gas, whereas bases don't tend to react with the active metals. And Acids can also react with carbonate compounds and they produce carbon dioxide gas, whereas bases tend not to react. Okay, so here's a few things that you can, properties that are going to help us to differentiate acids and bases as we explore them. Okay, a couple of definitions, and I'm not going to get too much into this. I think that it's, you know, we certainly get a lot more into this in grade 12, but I think it's important to kind of just see a little bit of it. And so first of all, the first person to kind of discover or to, you know, we've certainly been using acids and bases for centuries, but the first person to really start identifying them and categorizing them was this Swedish chemist named Arrhenius. And his definition, I've got it at the bottom of the page here. I've got a little summary of it. Basically, Arrhenius said, an acid is any substance that dissociates or dissolves to form H+ in an aqueous solution, and a base is any substance that dissociates to form OH or hydroxide in an aqueous solution. So I'll just go back up to the top. So Arrhenius, you know, he would have said this one right here, HBr, which we know is hydrobromic acid. It breaks apart, when you put it in water, it breaks apart into this H+ ion and the bromide ion. H2SO4, which is sulfuric acid, it breaks apart into the H+ and the HSO4- ion. And then here, this perchloric acid, HClO4, breaks apart into H+ and the chlorate ion, sorry, the perchlorate ion. And so basically, Arrhenius kind of started to recognize that all of these had the same characteristics, the same properties that we had just seen on the previous slide. And he also recognized these ones as being bases: lithium hydroxide, potassium hydroxide, and barium hydroxide. These ones all dissociate. When you put them in water, they dissociate into the metal ion and hydroxide. So basically, he characterized acids and bases as either forming H+ or OH. Well, a little while later, these two scientists, actually they worked independently, Bronsted and Lowry. One was English, one was Danish, I believe. But they kind of came up with a more general definition of acids and bases. And basically the Bronsted-Lowry definition is an acid is any substance that provides a proton to another substance. So we often use the term proton donor. Now you got to be careful with that definition, because chemists have been careful to point out that the term donor indicates that maybe they want to donate these protons. Well, that's not completely accurate, but certainly it's the substance from which the proton is removed. And the other one is a base, is any substance that receives a proton. So a proton receiver, I suppose. A proton receiver. Oops, IE, not, or EI. Okay, a proton receiver. And so Bronsted and Lowry cleaned it up a little bit and said it's not about hydrogen, the hydrogen ion forming, or the OH ion forming. It's all about this transfer. And they gave us this idea of conjugate acid-base pairs. And let me just show you this. So Bronsted and Lowry said, okay, well, if you put hydrochloric acid into water, it will donate its proton. Now, you're right, like its proton is in fact H+, but look what happens. It quickly joins with water and makes this H3O+. Okay, so it donates it and becomes H3O+, and then leaves the Cl-. So it's very similar, like, you know, it's very similar to the Arrhenius definition. Like Arrhenius would have said, well, HCl does this. HCl would dissociate into H+ and Cl-. And so, you know, it's a slight difference. Like, first of all, you can see that Cronstedt and Lowry figured out that, well, H plus can't exist on its own, and so that's why it quickly joins up with the water. But essentially, it's the same process. So a little bit more about these acid and base pairs. Notice that every acid has a conjugate. So look at this. It has a conjugate base, and what they differ by one hydrogen. Differ by one hydrogen. So look at this. Hydrobromic acid, its conjugate base is just the bromide ion. And look at this, the H2O has a conjugate, it's a base in this situation. Now, be careful, because water, I'm just going to show you here, I'm going to put a little, I'm going to highlight it. Water can take on the form of either an acid or a base. So look at this. In this situation, water is a base, but in this situation, water is an acid. And so just be aware that that's, you know, water can take on different roles, but it doesn't matter whether it's an acid or a base, they differ by one hydrogen. They differ by one hydrogen. So look at this. In this case, NH3, which is ammonia, differs from ammonium by one hydrogen. Ammonia is the base, and its conjugate acid is NH4+. In this case, H2O is the acid, and it differs from OH by one hydrogen. So I'm just going to put a little star there. One of your questions for homework asks you to write the acid-base pairs or identify them, and you'll know that they always differ by one hydrogen. Okay. So again, here's a nice little summary of the definitions of the Arrhenius definition and the Bronsted-Lowry definition. Okay. Just one last thing is, actually it's a fairly major thing, but it's to talk about strong versus weak acids and bases. And what I want to do is I want to go to a little applet here that we've, this is the PhET simulations, and I wanted to show you this. So first up, down at the bottom of the screen here, it shows the dissociation. And so in this particular case, it shows it's not any particular acid, it's just any acid. So look at this, it says if you had HA, and in your mind, you know, a lot of you are saying, well, Mr. Webster, A isn't an element, and you're right, but they're just using that as a placeholder. So let's say it's HCl. Well, if you were to place HCl into water, it's going to dissociate into Cl- and H3O+. So this is just meant to represent any acid being placed into water. Now, I'm going to show you a couple of things here. So first of all, I want to show you that if you were to dip in a conductivity tester, acids are very conductive, okay? And same thing with bases. Bases are very conductive as well. So we know that acids and bases are conduct well. All right, I'm going to get rid of my conductivity tester, and this is a pH tester, and I'm going to get more into pH in a second. But first of all, I want to show you what the molecules would look like. So here it is. Now, I'm going to put the solvent in for a minute. The solvent is water. So I'm going to put it, and you can kind of see they're in the background there. But I just wanted to show you that any discussion of acids and bases has the water that's there in the background. It's kind of, you know, constantly back there. But I don't want to leave it there because I think it kind of becomes a bit confusing to see that. But just know that the water is there. So this right here is a strong acid. And the reason why it's strong is that it fully dissociates. So look at this. Do you notice within this magnifying glass there are none of these, and I'm trying to circle it at the bottom here with my cursor, and hopefully you can see this, is that you see that there are these darkish molecules, a large one and a little one, and there are none of them in the solution. And that's because all of the acid has broken down into the blue and these red ones, into the two ions. And so a strong acid fully dissociates. So let me go back, and I'm just going to write that for you on here. So a strong acid fully dissociates, and dissociates just means dissolves, fully dissociates into its ions. Okay. So I've taken a picture of that app here. I also want to show it to you in its, in a graph form. And this is a graph from your textbook, but I thought it was a nice way of looking at this. Is that, look at this, is that it shows you that before dissociation, and really this is nice because it actually shows HCl, is that HCl, after you place it in the water, fully changes into the ions of H3O plus and Cl minus. In other words, there's no HCl's left in the solution. They're gone. It's zero, or virtually zero. And so I'm just showing you that a strong acid fully dissociates. The arrow that they're showing here, means that it goes completely over into its ions. Okay, so that's a strong acid. And you can think of it as something like, we've looked at table salt. Table salt, if you were to pour a little bit of salt into water, it would completely dissociate. It would completely break up into its ions. That's not always true for acids and bases. And so look at a weak acid. A weak acid only partially dissociates. Partially dissociates. In other words, a lot of it remains as the original molecule. And so let me go back to the, I'm going to go back to the little demo here. So look at this. I'm now going to show you a weak acid. And what I want to emphasize here is those blue and those red molecules are really what makes it acidic. Okay, and so look at this one. Oh, there's lots of them there. That's very acidic. It's very strong. It's going to burn your finger. Whereas in this case, if it's weak, not many of them dissociate. Look at this. You can see that there's a lot of the original acid that's still in solution. And so only a few of them have transferred over into the ions of A minus and H3O plus. And it's a good indication that it's a weak acid. Now, I'm going to come back to this to show you the pH. I don't want to use the pH meter yet because I want to explain what pH is first. But sure enough, if we go back to the, here into the note, you're going to see that they use this double arrow to indicate that no, it doesn't, a lot of them stay as the original acid molecule. And look at this. Here's the graph from your textbook. They've used something called acetic acid, which is vinegar. And look what happens. After they put the vinegar into water, most of the vinegar, in fact, about 99 out of 100 molecules, stays together. And so only a tiny amount, about 1 out of 100, will break into the H3O plus and CH3COO negative. So very few of those acidic ions form, and so that's why it's weak. And obviously acetic acid and vinegar in this case, you can put on your French fries, and so it's a weak acid. Okay, so there are actually only 6 strong acids out there. These are the only 6, and you got to kind of memorize these ones. These are the only 6 strong ones that fully dissociate: hydrochloric, hydrobromic, and hydroiodic. So those ones, remember, are our binary acids. And here are some of our oxyacids. We've got nitric acid, sulfuric acid, and perchloric acid. So there are many, many, many weak acids. Too many to list, but I'll just give you a few weak acids. Certainly, I've already told you that acetic acid is a weak acid, and that's that's vinegar. I'll just put here dash. Vinegar is a weak acid, but citric acid is a weak acid. Even some of our binary acids. Look at this, notice that it's got HI, HBr, and HCl, but HF is what we call hydrofluoric acid. It's a weak acid. Okay, so not all of your binary acids are strong acids. Hydrofluoric acid, H2S, which is hydrosulfuric acid, is also weak. But there are many, many, many. I can't get, I'm not doing justice here. There probably are, 100 weak acids. In fact, most of your organic acids, all of your organic acids are weak acids, and there's many, many, many organic acids. Okay, so most acids you come across are weak acids. Okay, pH. I said I was going to get into it. This is the last thing for this lesson. So basically, we use something, we talk about it as called the power of hydrogen, and it's called the pH. And what pH is an indication of the strength of an acid or a base. Sorry, one additional thing, I apologize, I'm going to go backwards just for a second. The same concept of strong versus weak acids applies to bases. So you can have strong versus weak bases. The same thing applies. If it's a strong base, it fully dissociates into its ions, and if it's a weak base, it only partially dissociates. Okay, so sorry to leave that. Okay, so pH is an indication of the strength of an acid or a base. But one thing I'm going to show you is that, first of all, even water itself breaks down into hydronium, which is this H3O, and hydroxide, which is the OH. I'm going to go back to the demo for a second. So let's look at water. So again, I'll show the water in the background. So you would think to yourself, well, water is very neutral, and you're correct. It is a very neutral substance. But even though it's neutral, it does break down into hydronium, which is the acidic ion, and hydroxide, which is the basic ion. But what's interesting about water is that it breaks into equal amounts. So that's why it remains neutral. Now, it breaks into a very small amount, incredibly, very, look at all the water molecules in the background here, and so few of these acidic and basic molecules, but there is enough of them. There's enough of them for us to see it. Now, look at this. I'll just show you this, is that, I know it's hard to say, I'm going to try to make this a little bit bigger, is that in water, there are 1 × 10⁻⁷ moles per liter of hydronium and hydroxide. So an incredibly small amount. Okay, so 1 × 10⁻⁷. It's point, and then 1, 2, 3, 4, 5, 6, 1. So that's 1 × 10. That's how many. That's the moles per liter of hydronium and hydroxide in water. Okay, so not very much. And so you can see that in a strong acid, it goes up to almost 1 times, it's basically just 1 mole per liter. And look at this, for a strong base, it's 1 times 10 to the negative 14 moles per liter of hydronium. But the problem with dealing with these numbers, and sorry, I show, it shows them right here in decimal form, is that those are hard numbers to deal with. And so that's why we use something called a logarithmic scale. And pH uses this logarithmic scale. And what a logarithmic scale does is it compresses the scale into numbers that have more meaning for us and are easier for us to work with. And so it's taken a scale that ranges from 1 to 1 times 10 to the negative 14, and it compresses them down to numbers from 0 up to 14. The only thing you have to remember is that an increase of 1 on a logarithmic scale means that it's 10 times more or less acidic. So as you go from, let's say, 6 down to 4 in terms of your pH, well, a 6 to 5 would be 10 times more acidic, and then 5 to 4 is another 10 times, so that's 100 times more acidic as you step twice. As you go from 11 down to, let's say, 8, that's 1,000 times more acidic. Or if you were to jump up from 11 to 14, it's 1,000 times more basic. So 10 times 10 times 10. So just be aware that on a logarithmic scale, you've got these big jumps. Even though they've made the numbers a little bit friendlier for us by making them only go from 0 to 14, you've got to remember that there can be huge jumps between them. The way you calculate pH, and you're going to have to do this for homework, the way you calculate pH is that you use a button on your calculator called the log button. And a lot of you probably have seen these over the years. There's a button on every calculator, but you would do the log times the concentration of the hydronium. And look what they use. They use square brackets. Which essentially just is the same thing as the capital C that we've been using. So our textbook uses both forms, but it's the concentration of hydronium that you take the log of it, and then you put a negative with it to get rid of the negative value. It's just basically, I'm going to tell you, your calculator, when you type in the log, it's going to show up as a negative number. Just get rid of the negative. And so if you were to find the log of 1 times 10 to the negative 7, it turns out that it's a pH of 7. So let me go back to our little applet. And sure enough, look at this. I'm going to get rid of the solvent just for a second. So here it is. This is pure water. If I were to dip a pH meter in, it would tell me that I have a pH of 7. It's neutral. Okay, what about for a strong acid? Well, a strong acid, again, if I dip it in, it's got a pH of 2. And so, it's much closer, it's much lower. The lower the value, the more acidic it is. For a weak acid, it has a pH of about 4.5. Look at this. What about a weak base? Now I'm over 7. So 7 is the dividing line. 7 is neutral. Below 7 is acidic. Above 7 is basic. Let's check out a strong base. Oh, it goes up to 12. And you can even go up to 14, but a strong base has a pH here of 12. Okay, so back to this demonstration or the slides here. I just wanted to show you, here it is, an acidic solution is anything that has greater than 1 times 10 to the negative 7, and that's the concentration in moles per liter of hydronium. So basically, it's any solution where you have more of the hydronium than the hydroxide, and your pH will be less than 7. A neutral solution has a concentration of hydronium of 1 times 10 to the negative 7. And interestingly, the same concentration of hydroxide. The two are equal, and so it has a pH of 7, and a basic solution has less than 1 times 10 to the negative 7 of the hydronium, and it would have greater amounts of the hydroxide present, so its pH is 7. I gave you a little scale here. Look at this. You can see that milk has a pH of 6.4. It's slightly acidic. Urine, rainwater tends to be slightly acidic. And then as you go down, tomatoes, vinegar, lemon juice. And then now you're getting into the strong acids. Stomach acid, which is mainly hydrochloric acid, has a pH of around 1. You can actually have a pH of 0, which is 1 mole per liter hydrochloric acid. Basic solutions, blood is slightly basic, it's 7.4. Ocean water is about 7 to 8.3. You can see detergents, antacids that you take for if you have indigestion, are 10.5. Household ammonia is 11.9. Here's lye, which is sodium hydroxide. It's another name for sodium hydroxide is 13, and so on. So you can there's the pH scale. Here's I just wanted to show you this, that this is similar to a homework question that you're going to have. Is it says calculate the pH of each of these solutions. Well, look at this. All you would do is type into your calculator 0.0027, and then you'd hit the log button, okay, on your calculator. And if you do that on your calculator will show, here it is, 0.0027. On my calculator, I have to hit second function, so second function and log 0.0027, and my calculator shows, it shows negative 2.568. But again, you just get rid of the negative, and so the pH of that is 2.56H. Look at this. In a cola drink, it's 5 times 10 to the negative 3 moles per liter of hydronium. So let's try that one. So look at this. On my calculator, I go second function log. So I bring the log up, and then I hit in 5 exp, and then negative 3. And I get a value of negative 2.3 is what my calculator shows, but we get rid of the negative. And so there you go. The pH of that cola drink is 2.3, and so therefore it's acidic. Remember, anything less than 7 is acidic. Okay, so try some of these other homework questions I've given you here. I've given you some from 10.1 and 10.2, and then I've given you answers here. Let me know if you have any questions. Take care.